My name is Andrew Ledbetter, and my project involved optimizing an ultrasonic atomizer for droplet ejection. The device is shown at the right and consists of a microfluidic channel that flows between a silicon chip with a microarray of pyramid-shaped nozzles and a vibrating aluminum surface actuated by a piezoelectric transducer. A focused acoustic resonance develops within the microfluidic channel with a well-defined time-averaged acoustic pressure field. The pyramid nozzles effectively focus the acoustic waves to create a high-pressure gradient near the nozzle tips. The physics of droplet ejection is very complex, and I will simply state that once the pressure gradient at a nozzle tip reaches a threshold value, the nozzle will eject droplets at a rate equal to the driving frequency driving piezo. A 2D conceptual cross-section of the device is shown at the right, with piezo, aluminum, silicon, and fluid layers. The thickness of each layer and the driving frequency are just a few of the many factors that play a role in the generated pressure field. The goal of this design optimization is to maximize the average pressure gradient across the nozzles in the array by varying the microfluidic channel height and aluminum thickness. Transforming this into an optimization problem, the cost function we are minimizing is a negative average pressure gradient across the nozzles, and the design variables chosen are fluid height and aluminum thickness. Since analytical solutions cannot be developed for a complex geometry, the problem will be modeled in 2 dimensions and ANSYS mechanical. There are 3 resonance modes that develop within the fluid channel between 500 kHz and 2 MHz. But due to the high computational cost of the problem, I limited the focus to optimizing the device operating at the first resonant mode only. The 2D finite element analysis domain used is shown at the right. The piezo aluminum fluid and silicon materials are represented by the light blue, magenta, blue, and purple areas respectively. The green represents a plastic boundary that holds the silicon chip in place. Here we can see the time averaged pressure amplitude of the 3 resonance modes within the fluid reservoir. The first mode corresponds to a half wavelength resonance, with dark blue corresponding to a pressure amplitude of 0, and the red corresponding to the maximum pressure amplitude, which is typically between 1 and 2 megapascals. The optimization method I chose to pursue was to create a response surface to represent the device operation. I ran 84 total simulations, varying the aluminum thickness between 3 and 4.1 millimeters and the fluid channel height between 0.9 and 1.2 millimeters. I used the quadratic response surface method described in Aurora's textbook to generate an approximated function f hat. Here we can see the quadratic surface response of the approximated function overlaid with the discrete solution shown as red dots. It is clear that the error of the approximated function is very large at each discrete solution. I also used MATLAB to optimize the unconstrained quadratic function over the design space and found an optimum at a 1.2 millimeter fluid reservoir thickness and a 3.218 millimeter aluminum thickness, which resulted in an average tip pressure gradient of 35.5 megapascals per millimeter. I compared this with the optimum discrete solution of 45.3 megapascals per millimeter, which resulted from a 1.15 millimeter thick fluid reservoir and 3.5 millimeter thick aluminum layer. Here I created a triangulation of the approximate solution and the discrete solution and plotted each contour. It's clear that the quadratic function provides a very inaccurate representation of the device operation performance. These plots just show just how nonlinear the device operation performance was, as one design variable was varied while the other was held constant. In conclusion, local minima of the cost function were determined by the response surface method and from the sample discrete solutions. Due to the complex and highly nonlinear behavior of the cost function, the quadratic surface response approximation was inadequate for this problem and resulted in an optimum pressure tip gradient that was much less than the discrete optimum. The global solution was not found. Unfortunately, not all the nozzles have a high tip pressure gradient at any given solution, and the average tip pressure gradient alone may not be an adequate quantitative determination for the device performance. In future work, numerous discrete solutions could be found over a larger design space, but this would be very time consuming. Thank you for listening.